right, so we're going to have two talks, more or less 30 minutes apiece. The topics, you just heard the titles. By the way, we're sharing the prize, but we didn't divide up the cash prize. So, at any rate, we're not that mean. All right, so I think we're going to start with you, Faryad. So please come up, and I think we have a microphone for you, so you free your hands. Sorry? Yeah, that's right. So just to remind you, the title is Surface Multiplasmonics, Fundamentals and Applications to Optical Sensing.
Okay. Okay. Thank you very much. Okay, so I would like to begin by thanking the ICO and ICTP for this award. I'm really humbled and honored to be selected for this award. I would also like to thank the award committee for choosing me for this honor. And my topic of today's talk is surface wave resonance and its applications in optical sensing. And as was told, I am from Lahore University of Management Sciences, which is a relatively new university in Lahore, which was established about 30 years ago. But its science and engineering departments were established about 10 years ago. And what we are trying to do there at LUMS is establish a program in science and engineering which is at par with the leading universities in the world. Okay, so before I begin with my talk, let me just give a little introduction of my research work. So I have been working on solar cells, plasmonic solar cells, which are nanostructured solar cells. And also I have worked on the solutions of Maxwell equations for anisotropic mediums like uniaxial, biaxial, and gyrotropic and other mediums. And recently we have authored a book on dyadic green functions in modern metamaterials, which are anisotropic in nature. I have also been recently working on photonic crystals, especially one-dimensional photonic crystals, which can also be anisotropic, and some work on hyperbolic, zero-index, negative phase velocity metamaterials is also being done in our group. But today's talk, which is also my major contribution in optics, is on surface plasmon Poynton waves, which are guided by nano-structured thin films, which are sculptured at the nanoscale to get the properties that we want. And also we will see their potential applications in optical sensors. I would also like to take this opportunity to invite you to submit your papers on optics to Optic. I'm one of the editor working with this journal, which is actually a 70-year-old journal. And here's a glimpse of the activities related to optics that we have been doing at LUMS. We have actually recently established a very active SPIE student chapter, which is doing outreach activities in nearby primary and middle schools. And we have also been actually motivated by the same optics school when I came here in 2015. And we organized a similar school in LUMS in 2016. And hopefully we will do it again soon. And we're also developing an optics lab from a grant from the government of Pakistan. And we have been running several seminars at leading universities in Pakistan, like recently established ITU, Punjab University, Faisalabad Agriculture University, and also my alma mater, Quaid-e-Azam University, where I did my undergrad. I have conducted several workshops on plasmonics and recently on anisotropic mediums, and also have been an invited speaker in Nathia Gali Summer College, which is one of the premier summer college in physics in Pakistan. So with this, let me begin with my talk. So I will cover in this talk the basics of the canonical boundary value problem, and I will discuss some of the work that we have done in surface multiplasmonics. And then I will go on to discuss a few results where we have learned how to excite these surface waves. And then I will discuss their applications in optical sensing. Now, surface waves are the surface electromagnetic waves which are guided by an interface between two different materials. We can have a material which can be a metal or a crystal or something, and then another material which is different than that. So there are a lot of types of surface waves, but the most famous is the surface plasmon or SPP wave, which is guided by a metal and a dielectric material. And that's what actually the most commonly known surface wave is, where we have free electrons in metal, and as the surface wave propagates, the electrons oscillate, so we call it plasmonic waves. So this wave is actually very important in plasmonics because it's bound to an interface which makes its wavelength to be much smaller than the free space wavelength, which means that we can probe structures that are smaller than the free space wavelength, so we can have sub-wavelength imaging. And because it's very localized to the interface, this is then very sensitive to small changes in the material properties near the interface. For example, something changes here or something changes here, it affects the characteristics of these waves a lot. So because of this reason, it's used in optical sensors, and because of its shorter wavelength, it's used in imaging at nanoscale. So this is a wave which is actually known for now more than 60 years. A lot of work has been done in plasmonics with this SPP wave. But almost all of the work until a decade ago was done on a metal and a dielectric, where they are both homogeneous, isotropic, simple materials. When I started work on it, so this was the state of affair, and our goal at that time was to see if we can increase the number of waves, because if we can increase the number of waves, we can have chemical sensors that can sense 2 or 3 or 4 things at the same time. If you have only one wave, which is possible when you have both materials which are simple, isotropic, homogeneous medium, you only get one SPP wave. And that is also p-polarized. You don't get any s-polarized SPP wave. And because of that, we have chemical sensor which sense one thing at a time. Or if we want to use this surface wave in communication, we have only one channel for communicating information from one side to the other. And also in solar cells, since only p-polarized wave is excited, s-polarized, which is half of the incident light, cannot be converted into cannot be absorbed by the solar cells. So idea at that time was to see if we can get multiple SPP waves at the same frequency. Now I'll come to that, and before that let me just introduce a little bit terminology. We call SPP wave when we have one side metal and the other side dielectric, and we call it Diakonov wave, which are actually recently discovered when both sides of the material are dielectric materials, but one medium is anisotropic. And then we have TAM waves, which are guided by an interface between two materials which are both isotropic, but one is periodically non-homogeneous like a crystal. And then Diakonov TAM waves are when we have nanostructured materials which are anisotropic and periodic. And then these Uller-Zenneck wave I'll briefly discuss, which were actually the first surface wave that were predicted in 1903. which also exists between two dielectric medium, but one is lossy, because initially people were trying to understand sort of radio wave propagation at the interface of earth and air, or the interface of sea, water, and air. So I'll have a few slides on this as well. Okay, so coming back to the surface waves, so there are three things that surface wave have to satisfy in order for them to be surface waves. One is that they should satisfy Maxwell equations because they're electromagnetic waves, and then they have to satisfy the boundary conditions at the interface. And the last condition which make them surface wave is that they should decay as we move away from the interface. So any wave that satisfies these three conditions is a surface electromagnetic wave. And we call it SPP wave if one side is the metal. And we can study these waves in several ways, but one of the basic thing is what we call a canonical problem, in which we take two material and both material occupy half space. So this is going to infinity, this is going to infinity, so that there is only one interface left to interrogate. So that when we get the solutions, there is no confusion if it is a surface wave or not. So let's see a few numerical results. So this is the simplest situation where we have a metal on one side and a photonic crystal which has a few layers in one unit cell, and it is repeating itself towards this side. And we see that for each period of the photonic crystal, we have multiple solutions. We have, like, say, at 0.5, 1, 2, 3 solution, at 1.5, 1, 2, 3, 4, 5, 6 solutions. So there are multiple surface waves that can exist at this interface instead of only one. So in usual case, when we have SPP wave, we have one surface wave only, and that also p polarized, but here we have both p and s polarized surface wave. It means we can use multiple channel for communication or optical sensor and other things. So this power profile show that the wave is localized to this interface. We can see the similar thing if we have, let's say, a magnetic permeability variation on one side. So here it's a metal, and then this side is a magnetic material. So if the magnetic permeability is varying, we still get multiple solutions. And here it's an example of a nanostructured material. So this is a sculptured thin film, which is actually chiral helices like this, which are too small to be visible here. So all these columns that you see, they're essentially these helices that are grown in this way. So even in this case, we see that at different wavelengths, we have multiple solutions of surface waves. So more than one surface wave can exist at this interface. So this canonical problem is used to tell us that what type of surface waves can exist at the interface. But of course, that cannot be used to excite the surface wave, because we assume this metal and the dielectric to occupy half spaces. To excite the surface wave, we have to use some coupling technique, and the simplest one is to use a prism. For example, this is actually the most common Crestman configuration which is used by people to excite surface wave. Here, when you have incident light from this side, the evanescent wave couple to this interface here, and the reflectance is reduced at this particular angle. So whenever we have a reflectance dip or the absorption peak, it means surface wave is being excited at this interface. So this technique can be used to excite these surface waves. So for example, here I have shown the absorptions for p polarized incident light, and we see multiple peaks in absorption, and each peak indicates one surface wave that is being excited at this interface of a metal and a Rougate filter, which is a periodic dielectric material. So instead of one, we have several p polarized surface waves. This shows the power profile on both sides of the interface. So we see that in the metal, the power decays as we move away, and in the Rougate filter, the power decays, but it decays periodically because the medium is periodic. Here's another example for TAM waves. Here, there's no metal, because this is a dielectric, but we see the same thing, that as a function of incidence angle, we see several reflectance dips, both for the p polarized incidence and for the s polarized incidence. So it means we can get multiple surface waves of both p and s polarized incident light. Similarly here, as an example of Diakonov-Tam surface waves, the difference between this and previous is that here we have a periodically non-homogeneous, but also an anisotropic medium. It's anisotropic because this direction is special in which these helices are growing. So we see that when we have incident light from here, we have multiple absorption peaks, and each peak, both for P and S polarized case, represent a different surface wave. So using this periodically non-homogeneous material, we can excite more than one surface waves, which means we can design optical sensors which can sense more than one thing at the same time. This is also the same Diakonov-Tam wave, but excited with an air porting materials, because this is important because we can replace this air with some fluid, and we can sense the refractive index of that fluid using the shift in these peaks. Here, it's a parametric study of the same thing, where we show that they can be excited in the prism-coupled configuration using an SNTF instead of a sculptured thin film, a chiral sculptured thin film. So here is actually the first experimental proof of those Diakonov-Tam waves that we were discussing theoretically before, where we fabricated the same chiral sculptured thin films next to a homogeneous material, and we see that there are reflectance dips that doesn't change when we change the thickness of this material, which means that a surface wave has been launched at this interface. Because if the reflectance dip changes, when we change the thickness of this material, it means it's a waveguide mode and not a surface wave mode. Because waveguide modes change when the thickness of the waveguide change. So far we saw that we have some prediction by the canonical problem, and those waves can be excited in the prism-coupled configuration. But not all surface waves can be excited in the prism-coupled. And actually, one of the example is this Uller-Zenneck waves, which are actually mostly called Zenneck wave because people didn't know about Uller's work for a long time. And Zenneck in 1907, he was studying the radio wave propagation at the interface of seawater and air, but Uller has studied the same thing at the interface of earth and air. Since earth and seawater, they're both lossy dielectric materials, so it's actually the same thing. So this wave, which was predicted in 1903 and 1907, actually people have been trying to find it for a century, and there was no conclusive proof because they was trying to excite it using a prism-coupled configuration where you shine radio wave directly on the Earth's surface, and these waves, they couldn't be excited. The reason is this, that their wave number is actually less than 1 instead of greater than 1. For SPP waves, we get a wave number greater than 1, but for Uller-Zenneck wave, we get a wave number which is smaller than 1. And we also first tried to excite it in prism coupled, and we saw that because the Bragg angle also comes there, so there was no conclusive evidence for this. So we shifted to the grating coupled configuration, and there's no, because we can have several non-specular mode which can excite the surface wave, so we were able to see their excitation in the grating coupled instead of the prism coupled configuration. So actually almost 110 years after the prediction of these surface waves, we were able to excite them using the grating coupled configuration. And the funny thing is this, that a couple of years later, after this paper was published, I got an email from the granddaughter of Uller, and she thanked us that you have discovered Uller's work, which has been forgotten by people. So you brought that into light and gave him the credit, even though it has been only being called Zenneck wave instead of Uller-Zenneck wave. Because she has actually commissioned a biography of Uller. So there was an author who was searching the citation of Uller, and so from that she came to us. So there was a lesson for us that whenever you write a scientific paper, always try to go to the earliest and the basic work that has been done on that topic, so that you give credit to people where the credit is due. Anyway, so this experimental work showed that when a canonical problem predicts that the surface wave should be excited here, we can see the same excitation in the grating coupled configuration, but not in the prism coupled configuration. So let me now present a few results on optical sensing that we have worked on. The basic principle of optical sensing using plasmonics is actually this, that you have an absorptance peak for some refractive index, let's say 1.127 of the dielectric medium. So when the medium changes, these absorptance peaks, they shift because the surface wave that is being excited here, it changes its characteristics. So the angle where the peak, where the surface wave is excited is shift. So that shift tells us the amount of refractive index that has changed. So with this thing, we can sense the refractive index of any species that is here. And before this multiplasmonic work, where we have several peaks, people used to have only one peak, one plasmonic peak, so there is only one channel to observe the shift. But now, with the multiple peaks, we have multiple channels to observe the shift due to the same refractive index, or we can have multiple analytes there that we can sense through different peaks. So let me present a few results. So for example, here we have a CTF, a columnar thin film, which has straight columns. And when we excite it using air, let's say the dip is here, and when this CTF is filled with water, that dip shifts, and this shift gives us an indication of the refractive index that has changed there. So similarly, here is the same thing, but with the sculptured nematic thin film instead of columnar thin film, and we can see that we can use this thing for sensing, and we have like 1, 2, 3, 4, 5 channels to observe the shift in the refractive index. We have been presenting the work with Diakonov time wave, which is excited at the interface of two dielectric material. So this actually affords us two sensing categories. When you have plasmonics wave, one is metal and the other is dielectric. So when you have to sense some fluid, you can only change the dielectric side, but metal remains fixed. But when you have a surface wave that is being excited at the interface of metal, dielectric and dielectric, you can actually change the dielectric on both sides. So the sensing is actually enhanced because you can affect the material on both sides instead of just on one side, which is done with plasmonics. So with Diakonov time waves, we can actually increase the sensitivity, and we have shown theoretically that the sensitivity is actually much higher using Diakonov waves than using plasmonic waves. We can go to, let's say, 82 degrees or 58 degrees instead of about 30 degrees per RIU. So this is the same thing in configuration 1, where we have this anisotropic dielectric here and the other dielectric on the other side. And we have this other configuration. So this one is configuration 1. So when you have dielectric, isotropic dielectric here, this becomes configuration number 2. And we showed that if you add 1% silver nano particles, not more, not less, you can increase the sensitivity of this sensor. And if instead of the nanoparticle, use a hyperbolic chiral sculptured thin film, you can increase the sensitivity to actually several thousands of degrees per refractive index units. For example, a small change in refractive index of 0.001 can shift the peak by 3-4 degrees in the absorption spectrum. And we can see that this enhancement in sensitivity is because the field is highly localized to the interface, even though it's oscillating rapidly. But since the field strength is higher in the hyperbolic film, so the sensitivity is also higher. So with this, I would like to conclude that the work has shown that the periodically non-homogeneous dielectric material can expose multiple surface waves, and not only SPP waves, we can have other types of surface waves that can be excited in the prism coupled configuration. And even though I presented results only for optical sensing, where we can use multiple peaks to optically sense the change in refractive index. We have worked on multi-plasmonic solar cells, where we saw that the efficiency of solar cells can be increased because of these multiple peaks in absorption. So with this, I would like to conclude and acknowledge my PhD and postdoc advisor, Professor Akhilesh Lakhtakia from Penn State, who most of this work was done with him, even though some later work we are now trying to do independently at LUMS. But his constant support has been a great source of career advancement for me, and also huge encouragement from, and still continue to be, from my MPhil advisor at Quaid-e-Azam University, and also my current collaborator Tom McKay at University of Edinburgh, and Dr. Sabi Anwar, who is one of the famous physicists in Pakistan. I'm really grateful to him for his mentorship. It's he who has inspired me to do outreach activities in optics in nearby schools, because he himself is perhaps one of the best outreach activities in Pakistan, where he's organizing a lot of science melas and several outreach activities for a wide variety of audience. And at the last but not the least, I am really grateful to my current and former students who have done most of the work that I have shown here. So with this, I would like to thank you for your attention. Thank you.
Thank you very much, Faryad. Well, the floor is open for questions. Anthony? Oh. Anybody got a question? Yes.
This is not really a question, it's something for the students. What is called here surface waves is also called evanescent waves. And some of our students already saw them in the laboratory. So evanescent waves or surface waves are the same kind of waves.
Yeah, thank you. That's great.
Thanks for that comment. So you guys in the labs, you've already seen this. All right, any questions? Okay,
this is probably maybe more a curiosity. Has anybody explored the effects of nonlinearity in this, nonlinear surface plasmons polaritons?
Yes, actually there has been a lot of work in nonlinear surface plasmonics, which is mostly with the homogeneous material. You have a homogeneous isotropic metal and a homogeneous isotropic dielectric medium, but the dielectric medium is nonlinear. And actually, the nonlinearity with plasmonics is much easier to work with than with free space, because when you have light passing through, let's say, a dielectric medium, its intensity is whatever you put in. But in plasmonics, when you couple light to the surface wave, the field is extremely enhanced near the interface. And because of that, the nonlinear effects magnify. I haven't done myself, but there's a lot of work that's been done on this area. Yeah, thank you.
Okay, any other questions, comments? Yep.
Thanks for your presentation. I have no question, but I have a comment. I think it would be nice if you could all of these theories by experiment to see the agreement between experiment and also theory. Just a comment.
Yeah, thank you very much. We actually have done some experimental work, and some of them is being still done at Penn State. Since I moved to Pakistan, as I mentioned, our university is only 30 years old. And in 2014, when I joined LUMS, the Department of Physics, which I was part of, was only 6 years old. And still, there were empty lab spaces. So we are now establishing the labs. And hopefully, in 6 months to 1 year, my lab would be ready. So we will definitely be doing experimental work. Yeah.
Okay. Any other comments, questions? Let's thank Faryad again for a great talk. Congratulations.